Okay, hello everybody. We're gonna watch this little sketch. This is from Genesis history. They made a couple of these, just taking everybody through and talking about it. And you know what? I do know this is supposed to be a documentary. It's really not, but anyway, that aside, this is Snelling. Snelling is one of the three with Austin and Baumgartner, who are also, like Whitmore, degreed geologists or geoscientists, PhDs, who have for some reason fallen into this young Earth camp. Snelling is a little bit different from the other ones. He has no qualms dumping his conclusions in front of you and then just cherry picking evidence, and if he even does. He appeals to emotion a lot more than the others do, but I don't want to do logical fallacies. I'm going to address what he actually says. He's also notorious for making accusations and questioning professional scientists' work with no evidence. Those of you that saw my Grand Canyon critique of his paper, his 2021 paper, will know what I'm talking about. If not, it'll be linked so you can look at it. Anyway, let's get started. Like I said, I've only watched a few minutes of this so I could get some background information for you. And, you know, let's just get started.
Every time I come to places like this, I'm overwhelmed again by just the sheer beauty of all of this.
It is. I mean, you look at the colors.
Okay, just real quick, for bearing, Sedona is in southwestern United States. I'll just show you where the town is. They're not actually at the town of Sedona, but it's close by. It's not that far. It's a park of some sort. I forget the actual name, but I know where it is. Sedona, Arizona. It's on the southern end of the Colorado Plateau. I'll show you that later. But I just want you to see where it is on Google Earth. It's almost dead center of Arizona. All right. So it is still on the Colorado Plateau. This is about the edge of the Colorado Plateau right here. So, or like this, something like that. But I'll show you later. Anyway, I just wanted you to get your bearings about where they are. They're over here. I'm pretty sure down here. So we're not really that far. This whole thing is pretty much Colorado Plateau right here. You see how it stands out, and see this topography here? It looks completely different from this. You have a lot of geology and tectonics going on here. Well, I should say tectonics. That makes everything here really complicated and makes a very bad place to make global extrapolations from, just because of the complexity. I'll touch on it a little bit here, but I won't get too much into it. All right, let's get back to this video.
But the important thing to note is that this landscape is actually very stable. I mean, the very fact that there's vegetation there means that there's stability. There was lots of erosion in the past to carve out this whole terrain, but those cliffs and the valley floor are very stable, which is why you've got the vegetation.
So that
I already know where he's going with this. He's going to say, well, it's stable today, but wasn't before, henceforth, catastrophic flood. However, that doesn't mean anything. It's been stable for a long time. It's still stable, but it's not craton. In geology, we refer to stable parts of the continent that are now stable and have Archean pieces to them as cratons. This is not a craton area. And, you know, it's stable in the fact that, yeah, it's not going to fall into the ocean in your lifetime, but in a grand geologic scale, it's not stable. And none of these plants look old. And it doesn't matter. Erosion happens. It's still happening. I mean, we'll see if we see any, you know, mass waste falling out of the cliffs here, and it's still eroding down here too. It doesn't mean anything. The topography and the stability, whatever that actually means, is not really even applicable here. It has nothing to do with anything that could have happened in the past. The fact that these plants are young tells you that we still have some sort of strong erosional force going on here, for lack of a better word. It has to do with the Colorado Plateau and its uplift, but let's just listen to him a little more here.
means that we had a catastrophic period of erosion, and then
Nailed it. No, doesn't mean you have catastrophic erosion. There's no reason to assume that. You have no evidence of that. You don't even know how to model that. To make a prediction, and because that's what actual science does. Makes predictive models that can be tested. But that was a statement.
It stopped.
That's right. Today, everything's much, much quieter. Today's processes are extremely slow, but they can't explain how we got this erosion, how we got these layers, how we got these cliffs.
Actually, we can. That statement was completely false. Let's go a little further, and then I'll give you a little bit of background. I don't want to cut them off too frequently.
This is, as it were, a fossil landscape that is a remnant of catastrophism in the past.
That's an assumption. See, he wants it to be a global flood. He's already dropping the conclusion, sitting there saying we can't explain this any other way, and just going on. That's complete. It's bullshit. I'm just going to say it. Okay, let's go on.
All right, so you were saying that you wanted to come here because you see evidence of a young Earth because of what's here. What do you see?
Yes, well, the first thing we notice is the extent of these layers. It's like a stack of pancakes. For example, the red unit that goes all the way across our field of view, that's the Schnebly Hill Formation. And above that, you can see the first white unit is the Coconino Sandstone. And above that, you've got the Turaweep, and at the horizon, you've got the Kaibab Limestone, which is the rim rock of the Grand Canyon.
I just want you to, just real quick, the Kaibab is in the Grand Canyon. I don't think this is. I know this is not the Schnebly, and the Coquina is in the Grand Canyon. Now, something young Earth creationists like to do is they like to extrapolate geologic units infinitely in every direction. You'll see that in the Baraboo video I'll do, or not my Baraboo video. There's another one. They talk about how there's just sandstone all of it, and it's not true. It's not true. And we're not even that far from the Grand Canyon, and we're already seeing different lithological units, because remember, we name formations, and you can have sandstone, limestone in there. It doesn't matter. We name it based off the lithology, the physical characteristics of the rock. We don't divide formations by time. So if there's a change in name, there's either a new unit coming in that's lithologically different, or another unit graded in significantly to be to a different facies enough where it's completely different, like a limestone grading into a sandstone laterally. And also something else you notice here, look at how level everything is. Now, I don't know about you, but I don't know about any catastrophes that lay down nice little layers like that ever. And this is obviously all Phanerozoic. I don't. Is it can't? No. We're up in the Permian here, so we're high up. We're almost into the Mesozoic, I believe. Yeah, something like that. Yeah. So you still got tons of unexposed Phanerozoic rock at the bottom. So let's move on here.
And here we are, 70 more miles from the Grand Canyon, and these layers are still here.
Yeah.
I just covered how they're not the same thing all the way through, but whatever.
And the scale is what's important. We're talking about the scale of the sedimentation. If we have a flash flood, it's only in a very localized area, and we're not going to get these nice, flat, continuous layers that we see here.
Yeah, you're not. And you have yet to produce a global model that says you would get nice layers that just happen to look like the same type of layers you would get in a transgressing marine sequence. So over a long period of time. So model, Snelling. I want a model, and I want it to be testable, and I don't want it to be the traditional model that everyone else uses, us geologists, and you just say, well, it happened really fast, because that violates the known laws of physics. So yeah, we need you to produce a testable scientific model if you're going to claim to be doing science. The second you inject the supernatural, you are no longer doing science. Hard science, geology, biology, chemistry, physics, all deals with the natural world. It doesn't deal with the supernatural at all. Supernatural is ignored. That's one of the great filters science has that philosophy does not. That's why science progresses a lot faster.
These layers go for mile after mile after mile. Take the Coconino Sandstone. We can trace it from here, right across New Mexico, Colorado, right over towards Kansas and Oklahoma, or even in Texas.
What did I say? I said he's trying to. This is bullshit. You can't do that. He said the Coquina Sandstone. Now, if I remember correctly, so I didn't get this far last time. Let's see. What do we have here? Let's pause this. I'll come back when I find it. So I know where Snelling's getting this. I found Whitmore's paper. I did a video on Whitmore, and I'm going to show something to you here. Then I'm going to show you how it's completely full of it. This is the paper, all right, that Whitmore did, okay? And, you know, look at where it was done. Now, they have a map in here. See this map? This map is supposed to be aerial extent of the Pennsylvania Permian sandstone sheet that can be correlated, and we're going to talk about that word, as a more or less continuous unit in the western United States. It includes the Coquina and a bunch of others. This looks a lot to me like this. Doesn't it look like that to you? And what did Snelling say it was? Let's see.
The Coconino Sandstone. We can trace it from here, right across New Mexico, Colorado, right over towards Kansas and Oklahoma.
Okay, so he said Coquina Sandstone, and the place he pulled this from doesn't even say that. Now, we're going to take a quick look at the Permian and Pennsylvanian rocks. So the impression that I get from Snelling saying that is that we have sandstone all over here. Remember, this stuff is higher in section than the Cambrian. Geologically younger. It's above the Cambrian by a lot. Let's see, between this we have, and the Cambrian, we have the Ordovician, Silurian, Devonian, and Mississippian. But let's go a little bit before I show you something.
Or even in Texas, we're talking at least 200,000 square mile.
He even writes it there. That's not true, Snelling. That's not what this says here, down here. That's not what this says. But let's continue a little bit.
For this one rock unit that's consistent for mile after mile after mile. That's not the scale that we see today with localized sedimentation. And to get it flat lying like this over such a large area, it's like you have to make your pancake all at once very rapidly.
Mm-hmm.
So here we go with the whole pancake thing, this oversimplified concept of geologic processes that young Earth creationists love. Now remember, we're dealing with this, Permian and Pennsylvanian. The Pennsylvanian is a subperiod right before the Permian. It's the subperiod right before it. We have Pennsylvanian deposits in Illinois and Indiana. You know what you don't see? Massive cross-bedded sandstones. At least you do see them in streams, but you don't see sheets. There's no large desert deposit like there is out west. Why? Because the geology changes. The Earth is not homogeneous. Now, if this covered everything, you might have a point, but it doesn't even. Let's first look at a general cross-section. Okay, this is actually, because, you know, young Earth creationists love to talk about pancakes, layer, basic 101 concepts in geology. Now, this is vertically exaggerated, but you look at it, you see units tonguing in and out. You see areas of not the same stuff. They left stuff out. There are units here, but they left them out because they're trying to show you something. But you see the inter-tonguing relationships. You see how you have different things. You see how unconformities are over here, and then this unconformity stops. Unconformities do not continue forever, just like conformities don't. And then, you have units that peter in and out, and then all of a sudden they become thicker and thicker and different units. See, this is what actually happens with these units. See, this is one sandstone. It's time transgressive. It was deposited earlier in one part than later. That's how sequence stratigraphy works. We know this. Everything's not simple layer cake geology that young Earth creation. Even in the layer cake geology, it's not that simple. I'm not even dealing with the Precambrian here. I believe the Dakota's Cretaceous, so we start to get into Cretaceous stuff. But you see, it's just the stuff changes. And, you know, like I said, this unconformity between these units here is huge. It's massive. Yep, there's Upper Jurassic. Sorry. Yeah, so the Dakota Sandstone's Cretaceous. But this here, this unconformity is huge, this one. And then all of a sudden, it just ends. Because we had active deposition going on at that time. Because just like today, you go off the coast of Gulf of Mexico, you have units being deposited, but here where I'm sitting, it's being eroded. We're creating an unconformity here, but we aren't in the Gulf of Mexico. That's how it actually is. And just so in case you guys want to see what this is, where is it? Oh, there it is. All right, so down there on the bottom, 2002, right here. Okay, now when you're presented a stratigraphic column of a state or a region, depends on the complexity of the state, it's simplified from this. They tend to look more like, that's the Grand Canyon, they tend to look more like this. Okay, it's simplified. This one is Wyoming. This one is North Dakota. We already saw that. Here's Kansas. Kansas doesn't have a continuous one. They just threw theirs online and divided it. But here's an old one. So, this is Arkansas. So you can see it's simplified. It's not as simple as everyone makes it out to be. Now, is this Wyoming? Let me go. I need to go get you guys Wisconsin's too. We'll come back to that. Wisconsin strat column. It's a big one. Stratigraphic column. I'm surprised I don't have it there. Let's see. It's the PDF's pretty big size. All right. They haven't really updated it, but see here. Let's look here. So we're going to start Wisconsin and move towards where he is. Now I want you to look here. What do you see? Oh, now I know. It's like because there's no Permian deposits. We have no Permian here. See, there's the Devonian. There's no Mississippian. There's no Pennsylvanian. Now, if we go south in Illinois and Indiana, there is. But we have no Permian there either. So we have a major unconformity here in Wisconsin between the Devonian and the glacial deposits. Some 300, these have changed since then, but about 350 million years of an unconformity. This would be considered a great unconformity to some people. And it's way above where they think their flood happened, way down here. So, yeah. All right, let's go to the Cambrian here. There are Cambrian. You can see we have different lithologies here. But I'm going to move west. I want to show you, let's see, we'll go to the Grand Canyon. Let's go to North Dakota first. Let's go to the Permian. Because they have more complete record because we had inland seas during the Cenozoic, Mesozoic, and late Phanerozoic. See Mesozoic. Here's your Permian in Pennsylvania. Now he's saying the Coquina Sandstone is traditionally interpreted to be a desert type environment. We think that because we see things, like mud cracks that don't form in the bottom of active oceans. So, there's reasons for that, and planar crossbedding instead of trough crossbedding, and the maturity of the sand, all that. But when you look at this here, and I went over here field camp, look at the Permian and Pennsylvanian. Permian, Pennsylvanian. Look at these formations. We have the spearfish, which crosses the Permian-Triassic boundary because it's based on lithology, not chronology. And we did study the spearfish. We didn't divide it out in field camp. But this here, look at the description. That's a siltstone. We have a limestone here. Let me zoom out a little bit. All right, so you can see a little better. We have this limestone here. Then we have a shale. Again, here's siltstone, shale, they're mudstones. Then we have a sandstone with limestone. And then we're still in the Pennsylvanian. The base, this unconformity forms an unconformity. So the Pennsylvanian is mostly dolostone and shale. These minor yellows are sandstones. That's it. So the only prolific sandstone unit between the Pennsylvanian and the Permian is this Broom Creek. So we don't have this widespread coquina that Snelling is talking. Oh, we went past it. All right, this. So we're up in Wyoming here, and there's no coquina. If it was coquina, they would call it coquina or coconina. I'm sorry if I'm mispronouncing it. Now let's go to Kansas. This is Paleozoic Permian. All right. This is their Permian in Kansas. Shale, sandstone. I think they're really creek. Oh no, dolomite. So sandstone, dolostone, shale. That's very typical of a transgressive sequence. As you know, a sea is moving up onto the land. And then we have the Day Creek. So we have this Marlow sandstone member, and then dolomite and shale. Funny, I don't see any coconina there. I wonder why. Oh, that's right, because it's not there. Now this is their Permian, so this is above. I believe that's it, right? Oh, they have their Permian divided out. This is the top Permian. This is the lower part. They have a lot more Permian in Kansas. But this is just to show you. So we have sandstone here, sandstone, salt plain formation, sandstone. So in the lower part, we have more sandstone, but we still have shale. We have the Blaine formation, which I do know is a somewhat complex unit. And here's your Dog Creek formation. Oh, what's that right there? So already we have sands. Now this is not a typical transgressive sequence. We have this one is, but this one is not. It's almost as if seas are coming in, coming out, coming in, and coming out, which is probably exactly what was happening. The Cedar Hill sandstone isn't even mentioned. Casper Formation, Webster. You saw this in the Wyoming. This stuff is not. Notice these names are even different. God, man. I don't know. Anyway, let's do another one just to show you I'm not full of it. This is. Oh, who is this here? Close. I don't need to edit you. This is Paradox Basin, which is on the Colorado Plateau, I'm pretty sure. But here you see Pennsylvania and Permian. You see the formations. Okay, so let's go down a little bit and let's see what we have here. These are aquifers, so we won't get into that. That's not necessary here. But here's your Permian, and once again, you have crossing time boundaries on here on the left. But here we have fine-grained sandstone interbedded with minor conglomerate and mudstone. That's nothing like the lithology of the coconina. Hard gray limestone, not even the same rock type. More limestone. Halite, salt, not as seen in the coconina. And interbedded limestone, dolostone, so, carbonates and evaporites, more halite. Red siltstone, sandstone, limestone, and shale just mixed in. None of this looks anything like the coconina. It's just not the same stuff. Which column is this? Sorry, I've seemed like I'm beating a dead horse here, but it's necessary to show you just how full of it they are. I believe the Paradox, I got to look up exactly where the Paradox Basin is. I apologize for that. Paradox Basin. So, let's see, we have the location here. It is located... where are you? I need to zoom out if I can. Okay, so here you go. Is this it? No. Yeah, well, it's over here. So it's kind of on the edge of the Colorado Basin. That's where I figured it was. So it is within the Colorado Basin. Yeah, see here? It's within the Colorado Basin. Okay, so stop saying that, Steve. All right. So one more. I'm just going to beat one more dead horse here with this. Which one is this? This is Oklahoma. Does he have anything in Oklahoma? Yeah, Duncan Sandstone. Let's see if we can find El Duncan Sandstone. It's also northern Arkansas. It doesn't change much. Duncan Sandstone. See, the Permian here is huge. Group Brentley trend. Okay. So we're looking here. It doesn't say, he doesn't tell you if it's Permian or Pennsylvanian. He just writes it there. Duncan Sandstone. I'm not seeing it. This is our Pennsylvanian. You can see there's a lot of Pennsylvanian deposits. I'm not going to sit here all day and look for it for you guys. If you see the Duncan Sandstone, let me know. But it would be, I'm here in the Pennsylvanian and Permian, and I'm not seeing it. Doesn't mean it's not there. Sorry I didn't prepare better for you, but I just wanted to show you, and I think I've already beaten the horse, that these units are not continuous over these areas that he's claiming they are. They're just not.
And so these layers show evidence of rapid sedimentation, the extent of these layers. If we dig deeper into the Grand Canyon, we get at the bottom, we've got the...
Just once, I want to see young Earth creationists not mention the Grand Canyon in a video like this. Just once.
Tapete sandstone. That sandstone can be traced right across North America, up into Canada, across to Greenland. We see the same sandstone with the same features and the same relative position in the stack of pancake layers across northern Africa all the way to southern Israel. So that's across one continent and found on another.
No. He's talking about the Sauk sequence, but he says Tapete sandstone. Tapete is a lithological unit. Do I really have to do this again? I'll be quicker this time. Which one are we in here? We are in North Dakota. It doesn't matter where I take you here. Here you have Cambrian. See, we studied all this. There's your sequence. These are not lithological units. Your Cambrian. I don't see Tapetes anywhere here. The Tapetes is at the bottom. So we're just going to deal with that. I see the Deadwood, which is lithologically very complex. So there's no... ever. Let's see. Let's go... No, we'll leave that alone. I'm going to close that now. Kansas. No, let's close those because I didn't get Cambrian ones. Let's go here. What do we see in the Cambrian of Oklahoma? We see... That's just a different name for something. Arbuckle. These are actual lithological units. I don't see any Tapetes. I do see some sandstones, but I don't see Tapetes. Wonder why. Now, let's see here. Now we can go to our Illinois and Wisconsin. And here we don't have... This is the Paradox Basin. We don't have any Cambrian, Ordovician, or Silurian. We have an unconformity. It was never deposited or it was eroded. So we don't even have that. Within the Colorado Plateau, the Cambrian Tapetes is not even complete there. So, all right, let's close that. I'm going to keep that open. I want to go back to Wisconsin's strat column for you, if I didn't do weird. Okay, so... we look here at the bottom of Wisconsin. This is Precambrian. This is my stuff I study. Also clastic deposits, these two. Anyway, Mount Simon. It is a sandstone, but it's not the Tapetes. And then we have the Eau Claire, which is shaly. And then we have another set of sandstones. We actually had an unconformity here. So these seas were not continuous everywhere. And then we get into Tunnel City, the Trump. There's actually a lot more sand in Wisconsin than there is even in the Grand Canyon. So let's try to do Illinois geologic map. See if I can get you the new one. Get your new one here. Let's, no, I don't want to go to images. I want to go to all. Yep, this is it. Bedrock geologic map of Illinois. I'm just going to this one for you, show you the columns, and it's going to page 2. You can see the geology of Illinois there, the bedrock. Most of it's covered by glacial, but you see here, this is recent. I believe this is 2000. What is this column? 2000, early aughts. It's IMAP 14. It's available online, obviously. And see, these things like Abroska, these are sequences. These are not lithological units. Mississippi and Pennsylvanian time units. They're not. And so is Carboniferous. These are not lithological units. The Tapetes is a lithological unit. It is time independent. And we get down here into Illinois, and we really should adopt Wisconsin's nomenclature. We have some of it. but not all of it. See, we have the Mount Simon too in Illinois there. I'm in Indiana right now. I don't remember if it's there or not. But you see, you get a lot of carbonates and shales too as you go up. And then you get even more carbonates and shales. So this is not continuous. That was my point. Okay. And we're going to come back to this guy here because this will really put a wrench in Snelling's conclusion backpedal lecture.
The continent at the same level with the same features.
Nope.
So these layers are very extensive, and that requires catastrophic sedimentation on a grand scale.
That's
nothing like we
untrue,
see
Snelling.
today.
It's almost hard to imagine the volume of material that represents.
Yes, in this case of the
It's hard to imagine because it never happened, because you would have to violate the laws of physics. And where's the big gouge outs? If you're going to deposit this, it had to come from somewhere, right? This stuff is clastic. It didn't magically precipitate from the waters. It's sandstone.
Coconino sandstone, for the area that we've been able to delineate, we're talking at least 20,000 cubic miles of sand. The scale of that, from what we can understand from the composition of some of those grains and trying to chemically match them with other areas where they might have eroded from, we're talking about a transport distance of well over 1,000 miles, probably as far away as from the Appalachians all the way out here to...
Now, that could be possible. I'm not going to deny you can get large transports, but the coconina is windblown. You're more likely to find that stuff in a fluvial stream environment, not a windblown aeolian environment. But, oh, he's going to start meowing at me. But anyway, so where was I? I just derailed. So anyway, okay, so we do know that you can get transports out. You can pull zircons from these deposits. You're not going to get an age like you would from an undeformed, unmetamorphosed igneous rock. But you will get detrital ages. Remember, the youngest zircons, that's as maximum age your sedimentary unit can be. It can be younger than that, just can't be older. But there's something else detrital zircons can tell you. It can tell you source area. If I get dates in a sandstone, let's say my youngest is 1 billion years old. Okay, so I know my sandstones that age or younger. But I get a lot of 1800s, like 1,800 million years, 1.8 billion. And there's nothing in the area that old igneous that it could have been derived from. But I'm looking 2,000 kilometers away, 1,000 kilometers away, and we have, say, Pinokian igneous rocks. Well, they had to come from somewhere, so possibly got transported that far. Is that possible? Yeah, it's completely possible. I mean, look at the Mississippi, right? Just look. It is, let's go to kilometers for you guys. Okay, the Mississippi River is basically from here to here, and we are talking almost 2,000 kilometers. All right, and the funny thing, though, is he's going to tout this great unconformity, and the bottom of the Phanerozoic is, you know, the bottom of their flood, the bottom of the Cambrian. But here's another thing. We pulled detrital zircons from Baraboo, and you guys have heard me talk about this before. You're going to hear me talk about it again. The papers are online, and I don't have it at the ready, or it's not online, but I can get it for you if you want to see it. Baraboo quartzite is here. There's other quartzites over here and here throughout Wisconsin. Then you had the Sioux here, which is a big one. There's a buried one in Iowa, probably one in Illinois that's never been discovered. Now, we pulled detrital zircons and we got really old ones, like 3 billion years plus. The only thing that could have been derived from is right here, but that's low-lying. It would have been covered really fast. It was level, very close to sea level at the time. So, and we find them higher in section. So there's only one other place they could have come from. Up here. How much of a distance is that? 2,500 kilometers. That's far more than what you see in the Mississippi River, and we suspect they could even have come from there. So, 3,500 possibly kilometers. So this is nothing new. And the Baraboo interval is Mesoproterozoic. About 1.5 to 1.6 billion years old, somewhere in there. A lot older than Snelling's Phanerozoic global flood. Yet we have these vast derived zircons. So were there 2 floods, Snelling? Oh, not to mention these quartzites are highly deformed. We had an orogeny, Baraboo orogeny. So, yeah. Let's just let him go for a little bit. I'm leading to something I want to show you, but
This area in the southwestern US.
So we have these extensive layers, not just across North America, but they extend into other continents as well.
No,
What
they
other
don't.
evidence do you
Yes.
see?
Well, the next thing we notice is
Strike
the
that.
boundaries between these layers. They're flat, featureless, knife edge. Generally, you can see the continuity all the way across the vista that we're looking at behind us. And we see the same in the Grand Canyon for mile after mile after mile. There's no evidence of erosion. You think about it. We're looking out here at a landscape where over time we've had erosion. It's still going on down in the creeks when there's the rainstorm. So if you imagine that there was a long time periods between these layers, you would expect to find topographic erosion features.
why? Why? Why would you? These are marine deposits and transgressive regressive sequences. You can get unconformities with just non-deposition. And if you take these over, like that cross section I showed you, it's not going to be continuous at the exact same chronological horizon. Lithologically, it's the same. But even at this scale, it's too small to see. You need to not just hyper focus on one location. There's no reason to assume you're going to see tons of topography. And there are places where you do see it. And when I do my Baraboo video, I'm going to take you to a place where there's a vertical depositional contact. You had the Baraboo quartzite, which has been turned vertical right up against Cambrian sands. And they're windblown, by the way. Right up next to them. So, yeah. And do you see erosional marks? That's Eric Hoven's favorite thing to say, and it's a non-thing. At that location, no, you don't. And there's reasons. But that's more complex than this here. You just had these sock sequence transgressions, regressions. You don't need to actually erode something to get an unconformity. As long as the seas didn't retreat too far, you're not going to get erosion. You can get hard ground. But some of these, I guarantee you, probably show evidence of erosion. I'm not going to sit there and say because I don't study this stuff. But I can tell you in other areas like Wisconsin, Illinois, the Upper Peninsula, we see evidence of that. You don't, but this is a normal, undeformed or not very deformed marine sequence. You wouldn't expect to see those. Now, as the sock sequence ended and the seas pulled out, you would get some. Now, but you're not even in that area. You're way up higher in the Paleozoic. You're at the top of the Paleozoic here. So this doesn't mean anything.
Very ragged looking.
We don't. We see knife edge, flat, featureless boundaries.
Young Earth creationists say this kind of stuff because they know you stand on the land and you see deep canyons and stuff like that. So you assume an unconformity has to look like that. And that's where they lead you. It's where Snelling's. You can't sit here and tell me that's not where he's trying to lead you. It's blatantly obvious. And so, if you don't know what these things are, the different types of unconformities, you're just going to swallow this because you don't know any better. So, yeah.
That tells us that the layers were deposited like a stack of pancakes rapidly, one after the other. The extent of the layers, rapid sedimentation, the lack of erosion between the layers means that you have to have them sequentially laid on top of one another very rapidly.
We saw that a lot. I remember when we were in the Grand Canyon, it was just these layers at knife edge.
That's right.
And so what you're saying is that if there is a long period of time between them, then there should be jagged edges in there and valleys.
Correct. Actually, the Grand Canyon does have some of those, and on top of the Precambrian, Cambrian unconformity, there is topography. But this doesn't mean anything. I'm probably going to start skipping some parts because I know this is getting long as it is.
And we've got an excellent illustration of the point here. We've already highlighted that red
But you're not even in that part.
sandstone, the Snebly Hill Formation.
Yes, but that doesn't sound familiar to me.
No, that's the Snebly Hill Formation.
Yeah,
it's not in the Grand Canyon. In the Grand Canyon, we go from the Coconino into the Hermit Formation. There's that knife edge boundary between the Coconino.
We call that a contact. We don't say knife edge boundary. That has no meaning.
Now in the Hermit Formation, and there's no evidence of erosion there, which means that the Hermit Formation was rapidly deposited. And
okay, I went over this in my last video, but let's see what he has to say here and see.
then immediately the Coconino was a deposit on top of it. But here, we've come 70 miles from the Grand Canyon and we've got this Snelling Hill Formation between the Coconino and the Hermit. And this Snelling Hill Formation, 800 to 1,000 feet.
It's about 300 meters.
Over an area of 1,000 square miles, had to have been formed very rapidly. If that...
He just sat there and told you how all these things are found on other continents. That the Pete's is here, that's there, and then he's showing you how you get other units within or between other units.
Took millions of years. We ought to see millions of years, evidence of millions of years erosion back in the Grand Canyon at that same boundary. We don't.
Post-editing Steve here, and I found this paper. That's the name, the author, the year. Now, what you're going to see here is I have to give you a little background on this because I don't want to leave you hanging. You see, this is a cross-section. It's somewhat generalized. It's to show you something, and I'll get into here in a second what that is. Now, here you can see Permian, bird shipping formation. You see all these lithological units. And you see it's a general cross-section from southeast Nevada to Casario Creek, and here's Western Grand Canyon. The brick-looking stuff are your carbonates. The dotted stuff is your sandstone. Where there's nothing, that are your mudstones, shales, siltstones, things as such. Now you can see down here is your scale, your horizontal versus your vertical. There is vertical exaggeration here, and a lot of it. If I was to condense this to a 1-to-1 ratio, these beds would look nearly level. Kaibab limestone here, formation here, and this is your base line. It's your top. Now you can set these cross sections to that to highlight certain things, and that's what was done here. And you can see the squiggly line, which is an unconformity, is here. Now you see them in other places. Now I went and colored some things for you to show you some stuff, and here's essentially the Grand Canyon. If you were to go there, that's what this would look like. And he was over here in Sedona. You can see we have two different sections here. Now, that's basically what was done here, is you took a lot of columns and connected them. But what do you see? I was right in my assumption that they weren't being truthful about the Snelling Hill Formation. It doesn't just pop in there. That's not what happens. So here you have the Hermit Formation, and it grades into the Supai Formation, upper and lower. That's not proper nomenclature, but it was divided out for a reason, because you have this local unconformity here, but it's the same formation. See, it's based off lithology formations. They're not based off time units. But what you see here is the Hermit, number one, it intertongues with this sandstone here. But it doesn't intertongue with the coquina. What you have here is a sharp contact, but there's no unconformity here. At least if there is, it's not a big one. It wasn't even drawn here to worry about. So it's just the time of non-deposition. And you come over here, and what do you have here? In the Western Grand Canyon, you have a little bit of high ground, but over here in Sedona, you start to get into a basin. There's a basin, and that's what's being highlighted here. So the Hermit Formation thins. And like I said, geological units like unconformities don't continue forever, despite what young Earth creationists say. And you see the coquina actually gets thicker. In the basin, it's at its thickest, and then it gets thin again, and off to southeast Nevada, it pinches out entirely. And what's here between there in the basin? The Snelling Hill Formation. Because you have a local topographical variation, which the young Earth creationists deny exist. You heard it out of Snelling's mouth. That, there's no topography, paleotopography, but there is. And the Snelling Hill actually intertongues with the coquina, and I thought it might intertongue with the Hermit or something, but, that was before I found this paper. And see, that's what they do. I do this stuff, and I had a hard time finding this paper because I don't know the area. But I did find it for you guys. And that's what young Earth creationists do. They present this 101 level concept for you because they know most people, that's as far as they go in geology. So they'll sit there and they'll say, well, pancake, layer cake geology, and these things extend forever. Because when you're taught at a basic level, you're taught the simplest scenario first so you can understand the concept. That's how that works. That doesn't mean that's how the earth is in actuality. We do that in everything. We do that in physics. We do that in chemistry. We do that in biology. We do that in all the sciences. So you could understand and build. So it's easier for me to build on your knowledge instead of just dropping this bomb on you and you're like, what? See, that's the advantage to higher education or, honors classes in high school, is that you start to learn this stuff. And if you haven't taken it, you're not going to learn it. Now, you might be apt at looking things up on your own, and more power to you. I wish more people were curious like that. But the average person isn't going to do that. They're going to take whatever their biases say, backs up their biases, and they're going to run with it. And the Earth is this complex system. It's not this simple layer cake thing that they portray, the geologic units continuing across continents, because it doesn't happen. That's not factual. Okay? So you have to understand that if you just have a basic understanding of geology, I can see why you would buy this young Earth creationist stuff. But that's not how it is. You have to go deeper than that. You can't just sit there and assume they're telling you the truth, because I don't want to call them liars, because most of the time they don't lie. What they do is they leave things out, like this. This is important. You can tell. See, you have paleotopography here. It just wasn't noticeable at a human scale. That's why we make these things over, 400 kilometers sometimes. It's so we can get the actual picture and how these things relate to one another in reality, and we can use that to figure out other things like paleo environments, paleotopography. Was this basin, how big was it? Because if I did this at a 1-to-1 ratio, you wouldn't see any of this. But it is there. Vertical exaggeration just highlights it. The topography wasn't huge, but it was there. And you get that in a lot of basins. You get that in the Illinois basin too. But, these are isolated, or not completely isolated, but near isolated basins. So the sedimentology changes. If we had this one rip-roaring thing, just flood going over the planet, number one, we wouldn't see stuff like this. That whole thing of layers being deposited, it makes no sense, because the sandstones are deposited in a different environment, and the carbonates are this and that. Usually when you have carbonates deposited, it's because you have a stop of clastic influence and the water chemistry's right. But if that sandstone comes back in, the carbonate factory gets shut off. So this is not as simple as portrayed. Anyway, I think that's it. Let's get back to the video. Because you can change lithologies when you change sedimentary environments. Sitting there assuming this is one sedimentary environment creates a paradox in your mind. And it shouldn't be. This shouldn't even be here according to Snelling, because it should still be Coquina or Hermit, because that's what he sees in the magical Grand Canyon. So this actually hurts him. But if you sit there and you understand geology and earth processes, this is a non-issue. So he's presenting what I guess people will call straw man, but I don't even think it's that. He's sitting there, starting at his conclusion, trying to jam things in there. And if you don't know anything about geology, you're not going to know this is a non-issue. It's just not an issue. So let's continue on. Here's something I want to show you.
So that means that Schnebler Hill Formation in this area here. So, and if we use that, in 5 to 10 million years, we'd have much, much more than 800 to 1,000 feet here.
Why do you think that, Snelling? We don't do depositional rates anymore because they get us into trouble, especially classics, because of changing environments. Faster transgressing seas, deeper basins. We can take a guesstimate if we have bounding conformable units, especially if they're dated hard igneous rocks. So I can do this with the Arano group, but you can't do that here. There's no igneous rocks here, Snelling. You can't even do this. You have no leg to stand on. You don't know if this stuff was deposited in 100,000 years, definitely not 4,500 or a year, definitely not a year, but 100,000, a million, or 10 million. You don't know that. You can guesstimate based on other things, but you do not know.
So something doesn't fit. Either the sedimentation had to be
See, here's that fake paradox he's putting in there that doesn't matter.
far more rapid than modern sedimentation rates, or
Just to let you know, Snelling is not a stratigrapher. He is not a sedimentary geologist. He is not a geochronologist. He is a petrologist, and he does decent petrology work. But this is not his subdiscipline at all. This is the stuff I study.
you had to have erosion off of.
In the Grand Canyon,
So the limestone lies erosion. That's right. And it's not
millions and millions of years missing, according to the conventional paradigm, in the Grand Canyon, but there's no evidence of erosion.
Doesn't need to be evidence of erosion to have an unconformity. Like I said, the Schneebly Hill could just in her tongue. I don't know.
That's right. And it's not just this example. If we go deeper into the
No, that's definitely some sort of feature.
Grand Canyon, we find the Temple Butte limestone lies directly on the Muave limestone.
This doesn't look very consistent with me. It looks like we have, I don't know. That looks like an unconformity to me. These units do not continue. You see cross, but you can get cross bedding in limestone. It does happen. But this doesn't look the same. Let's see what he's got to say about this.
Again, you can see in many places a knife edge boundary with no evidence of any erosion.
Did you just say it was flat? Knife edge. And then you show something that's not that way.
They claim there are 140 million years missing there because in other parts of the world you've got other layers.
I don't think it's 140 million. They like to exaggerate this stuff for some reason.
Between them. But there's no evidence of millions of years there either. So
it doesn't matter. We've already covered this. Let's move on.
We talked about right across continents and between continents, you've got this consistency.
You just sat there and said consistency. Then you brought in the Schneebly, which is inconsistent with your talking points. And then you sat there and keep saying knife edge level, and then you show something that's not a knife edge, that actually shows evidence of erosion. This is just, man, they're really insulting your intelligence here, people.
Well, Andrew, even though we have those very thick layers, within them we have these smaller layers. It's kind of like what I saw at Mount St. Helens. What's going on with those?
Just say Mount St. Helens, you can get bedding in igneous rock, like lava flows can be bedded, ash flows can be bedded. But this is just bedding. Let's see what they have to say about this.
Well, that's a good case in point. At Mount St. Helens, we had over a 20-foot layer.
Mount St. Helens is another one of their go-to places because obviously it was a catastrophic eruption. But I don't see what catastrophic volcanism has to do with flooding, with water lane deposits, classically derived. This shit's all igneous. It's not even the same rock type.
Deposited in just a couple of hours, but the sediment flow
Means
within
nothing.
it, the grains sorted out into these laminated layers that were.
And we'll argue about whether this is sedimentary or igneous, but it doesn't matter either or.
Different grain sizes. We see it here on a.
Yeah, different grain sizes. What did I see there? I see things that look like cobbles, stuff like that, different grain sizes. What do I not see in the coquina? Oh, that's right, different grain sizes.
In just a couple of hours, but the sediment, there was the critters getting in there and burrowing and turning it all over. It'll be all messed up. It wouldn't be nice, and periods was within weeks, inches thick. Back in 1980, there was a hurricane called Hurricane Andrew on the east coast of the United States, and it deposited a sand layer 6 inches thick.
Yeah, 6 inches, and it was a pretty big hurricane. But that's not true either, but we'll just go with it.
Now, within a few years, when the geologists went back to examine this layer, the layer had been obliterated. Why? Because within weeks and months, critters start burrowing into it. We call it bioturbation. They start turning it over. So that means if there was long time periods for these laminations to form within the large layers, you'd have the critters getting in there and burrowing and turning it all over. It'll be all messed up. It wouldn't.
You actually do get that. You get worm burrows and stuff like that in the Cambrian sandstones of the Grand Canyon in here and other marine deposits throughout. And there's even, I believe it's the Baraboo video, it could be wrong, where Austin even admits this. So this supports nothing. You see bioturbation in the Grand Canyon. You see it in Wisconsin. I can even hopefully I can find the boulder again and I can show you bioturbation because it tells you which side was up. It's a upping. Oh man, my brain today. It's an upward oriented indicator. Let's just say that. Okay. But here's something else too. Now, if that sand layer was eroded, it wasn't eroded by critters. It was eroded because it was deposited on the land, and the land, it's not normally marine, so it's going to get eroded. And are you going to notice any unconformity there? Would you even know the hurricane happened? Probably not. 100,000, 200,000, 2 million years from now? No. You probably never even know it was there because not every hurricane gets recorded. Once in a while, they do. But he's just talking about things and he's putting his foot in his mouth. And I don't know. Anyway, let's just go.
Be nice and neat. What you saw at Mount St. Helens was nice and neat because it was rapid. In one afternoon, in 3 hours, whoosh, all this material, this one layer, 20 foot thick, was deposited.
But it's not level like that across the entire area. They're just snapshotting it. That's their favorite thing to do. Take a local snapshot and extrapolate it to the nth degree.
And within it were all these bands. And the date is that you had underwater sand waves were moving along. The comparison is in a desert. Most people understand a desert with a sand dune and the wind blowing the sand forward. Well, underwater we see the same thing, sand waves. And so...
Yeah, you do. It can be hard to tell sedimentary environments, but there's other indicators.
The water current is rapidly moving it along, and what we get left behind are these front-facing slopes. And we can estimate the depth of water, the speed of the water current, and we can do...
Actually, you can't. That's a massive problem. First, you got to be able to reproduce these massive crossbeds in the lab to begin with, or some sort of mathematical modeling that will make a prediction, and they don't have any of that. He's just saying stuff now. And if he does have it, they haven't shown it to any of us. I've seen in their papers where they put stuff in there, but that's a model. That's a prediction. That's not an experiment. You've got to have some sort of basis for that to model it that way. I can mathematically model a stop sign growing out of the ground, but it doesn't match what I observe. So it's bullshit. Okay? You just throw it out because if it's not representative of reality, it's garbage. So I want you to look real quick here. Notice in the water, you could even tell there in the sand grains that those ripples are not very big. Now, these are not giant ripples. You can see massive cross-bedding here, and you see trough cross-bedding here. I don't know what unit this is, but this looks Aeolian to me. You get these high angles, assuming this has not been tilted or deformed, although it does look like it's dipping a little bit, a couple degrees, not a big deal. But you'd be hard-pressed to get something like this in any sort of marine environment, let alone a catastrophic one.
We get left behind.
Well, Andrew, the Coconino sandstone is a big issue because the conventional paradigm has for years said that this was formed in dry conditions.
Yes.
Even if the coquina was formed in water, which it wasn't, but even if it was, because you got things like mud cracks and huge dunes, it means nothing for young Earth creationists. It does not mean the Earth is 6,000 years old. It does not mean there was a global year-long flood 4,500 years ago. It doesn't mean that. And it's one unit within the Permian. It's not this entire thick thing throughout our entire geologic time scale. So
it's given as the textbook example, and it's held to tenaciously that the Coconino sandstone formed in a dry desert sand situation. Those crossbeds, everyone agrees that they formed as a result of dunes, but whether it was in air or water is the question. Now, we've examined this issue extensively. Steve Austin's student, Dr. John Whitmore, has combed the hills around here with his students, hundreds and hundreds
Yeah, Whitmore's a biologist.
of measurements of these crossbeds. And they all come.
And we did Whitmore's video, and he is not a structural geologist. So he was teaching you how to get dip, but that's not the proper way to do it, but I'm not going to ding him for that. This kid, I don't think he's measuring the right thing. Oh, he might be. So you got to be careful measuring crossbeds.
I'm in the range of 15 to 25 degrees, which is right where it should be with a underwater sand deposition.
There's some more than that, you can tell. So it doesn't.
Added to that,
It's going to get in the footprints watch.
in the Sedona area, we find these strange folded units called parabolic recumbent folds. This is where the water current was so swift that it turned up.
Parabolic recumbent fold. Now, this is structural geology. I don't know what unit this is in. I don't even know if that's what this is. This could be due to Sonoma may have some sort of tectonic thing going on. I don't know. It is on the edge of the Colorado Plateau, so that wouldn't surprise me. But these things are tectonic. They're not depositional, and we can demonstrate that. I don't know if that's even what this is. This could be a big-ass Leidsing ring for all I know. So, because as we've already demonstrated, Snelling leaves stuff out and says stuff that has no backing to it. And I do see what looks like conglomerate here. But anyway, I seriously question this is how he's portraying it. But let's do something while I'm still thinking about it for you guys, because I want to show you the complexity of the geology in North America and just show you this isn't nice layer cake stuff. Where the geology is relatively level, you do see it takes over large areas, but you look at stuff and you're like, whoa, then none of this looks like that. But first, let's get to this here and show you how it's broken down. There's our scale. North is the top. This is 2005. Okay. Now, they do have this broken out into units and stuff, but that's a different thing. See, what I do want you to notice, too, is you notice the oceans are completely different than the continents. This is what I would expect in layer cake transcontinental units, because these are lava units. Doesn't matter if they're igneous or sedimentary. Lava units on the surface are deposited level, relatively level, just like sedimentary units. So I'd expect to see stuff like this, and I don't. Now, our Colorado Plateau, I really wish I could just move that, is over here, Lake Winnipeg, so we're down. Okay, so our Colorado Plateau, where's Arkansas River? I see it. Man, I'm sorry, guys. I don't mean to do this to you. Oh, it's right here. Here's our Colorado Plateau. Even compared to the stuff just to the east, which is relatively level, T is tertiary. And that's Pennsylvania and the double P. We have tertiary. But even in this area, you can see it's not completely level. There's some topography here. But then you come over here to just to the west and south of it, and it's this entirely different looking thing. That's odd. The Colorado Plateau is between something that looks and this is something else, but it's not relevant for here. But it is tectonic in origin. But then you look to the east, you see these relatively level, undeformed deposits, and then you look at the Colorado Plateau, and it has some deformation, not too much. And Sonona's down here somewhere. Was about middle of Arizona, so it's barely on the plateau. So we have stuff going on here. But what's all this? This is the Basin and Range province. So here's your Colorado Plateau, and here's your Basin and Range. This is an area of active extension. The continent is trying to split apart here. Whether it will or not, I don't know. That's why you get all these lavas in this area. Because the continent's trying to rift. It's trying to do that. Because you have a plate that's been almost totally consumed riding under here, and then you've got right over here, you've got, well, let me zoom out so I can find it. Yeah, down here, So here's your basin and range, but down here you've got the East Pacific Rise. This is a rift. It's an old rift. The rift is expanding, widening faster than it is in the Atlantic. Whether or not the continent will shut this rift off, because that does happen, you can subduct rifts. I know it sounds weird, but you can. Or if the basin and range is trying to adjust for that consumed plate and will successfully rift, I think it will. And I think the Yellowstone caldera will serve as a triple junction. But anyway, so you have active rifting here. So this whole thing is massively, massively complex. And then you move east more, and here's Illinois and Indiana, you get the East Interior Basin or the Illinois Basin. And in Wisconsin, you don't really have a basin. You have the Wisconsin Arch, connects to the Kankakee Arch, comes down to the Cincinnati Arch. But here's a basin. It's the Michigan Basin. Here's the UP, which is totally different. And then you have your Appalachians over here, your Grenville. You can see none of this is simple. You have little areas that are simple, like this is the, what do you call it? Coastal plain, so it's relatively simple. And then you have Florida, which is basically a bunch of pile of dead things and some sand. Yes, I live in Salton, Florida. So this is totally different. Totally different. And this paper by Karlstrom, who actually does study this stuff with these other people who are actually structural geologists and actually tectonic people and geophysicists, we are moving back to an old idea. The Colorado Plateau is an area of uplift. It's probably been uplifted because of everything that's going on around it. We think this paper says that this might be an area where the mantle is going down, it's convecting the other direction. So that's going to pop this up, because the Colorado Plateau, the stuff is still relatively level compared to the basin and range and this stuff to the east. So, you know, let's see what he says here. Seeing the conclusions, what's said. I'm not going to beat this. Oh yeah, here's our, rebound, isostatic rebound. See, here's our internal cross-sectional model. And here we have your Southern Rockies, the mountains, the Great Plains, Colorado Plateau. And here we have rising magma. See, we can measure this stuff. And we have all of this stuff is modeled. So surface parameters, post-Cretaceous, read it if you want. But basically, it's because of the mantle convection, essentially, what's going on in the mantle. And we know that, too, because of stuff like this. I mean, it's reflected on the surface. The crust compared to the mantle is nothing. So any deep-seated mantle changes are going to be reflected in the surface. And like I say, you have rifting here and overriding the rift here. And you have the Transform Fault, San Andreas Fault, your East Pacific Rise. This is the consumed plate. You've got active rifting going on here. You've got volcanism going on over here, which is actually probably part of the rift. Your Colorado Plateau here is caught in the middle. This is your craton. This is your craton. This is your stable stuff. It wasn't always that way, but it is now. So this is totally unstable. On a piddly little human lifespan, it may seem stable, but it's not. This area is under dynamic change, and you got all these accretionary terrains. Terrains would come in, connect to the continent, so forth, so forth. We see that here in the Pinocchian 1.8 billion years ago. So this is not simple stuff.
Over the edge of the top of the dune.
Kind of like you see a wave when a wave curls?
Yes, when a wave curls and crashes. And we don't see that in a desert sand dune situation.
I don't know of any water situation that'll round a sandbar either, so Snelling doesn't matter. And like I said, I'm pretty sure you're probably misrepresenting this.
John Whitmore and his students have examined hundreds of thin sections, looking at the grains, looking at the minerals, and all of those features indicate underwater deposition.
Now, that's just a statement. I do know it's a quartz arenite, and I do know it's pretty clean. It's pretty sorted, which is typical for aeolian wind-blown environments. Not always, but it is. Like the St. Peter in Illinois is about as well sorted of a sandstone as nature can do. It's almost all quartz aranite. But the only surface wind-blown aeolian parts are Starved Rock member. The rest seems to be marine. We do see burrows in it and stuff like that. So, but the St. Peter, the Tonti member, I believe that is, it doesn't have massive crossbeds in it. It looks more like a more level marine sequence. Now, Starved Rock member has a lot of crossbeds, big crossbeds in it at Mathiasen State Park and places as such.
You'll be familiar too in the Grand Canyon. There's
Oh, yeah, here come the footprints.
evidence of little critters that walked
I've seen those.
on some of those crossbeds. And they're always going uphill, up the front face. It's as if the critter is getting buried by the water. It's trying to go up.
Well, I don't know how a catastrophic flood isn't going to rip that critter straight up from the bed and make its day miserable. I don't know how an amphibian or reptile can, walk it. What did they say? How fast? 2 to 5 meters per second? So wave coming in. And I don't know how they just manage. So that would actually imply that your coquina was already there before the water came in. I mean, none of this makes sense, and it's Permian. It's way stratigraphically above any of the Cambrian stuff in the Sauk sequence. This makes no sense. And those of you that saw my last video, or recent, I think it was my last one, the Whitmore one, where I showed you I can make footprints like that in relatively dry sand. Not perfectly dry, there is no such thing as perfectly dry, but in stamped sand. And with the more moist the sand becomes, the harder it is to get, good footprints because you actually crack the sand. And not to mention, you're going to have all these turbidity currents. He just showed you something he said was a big, huge side thing from rapid water, yet you get tranquil footprints. That doesn't make any sense, Snelling. It makes no sense. So whether the coquina was water lane or aeolian has absolutely nothing to do with your Noachian flood.
You can see the sky up there above the water, and it's trying to get up there. Interestingly, many of these, the claws are at a slight angle to the direction that they're trying to go, means they're bracing themselves in the water current. In some places,
There must have been some mighty slow current, which is possible, but it's not a global flood velocity. And like I said, only humans are dumb enough to walk directly straight uphill. They could be walking at an angle because they're amphibians. They're four-legged creatures. They don't walk with their legs tucked under their body. They're sprawling animals.
they've been knocked off their feet and left, right, and then stops, and then you see it again some distance away.
Yeah, because if the sand is compact and hard, it's not going to make a print on a 1 kilogram or 2.2 pound animal. I mean, I showed you guys that in my last one. I'm, almost 130 kilograms, and I wasn't leaving that big of footprints in the hard, compact, dry stuff. So that doesn't mean anything. And you would get stuff like dry, hard, compact stuff. You should be looking for things like desert pavement and stuff like that. And this here looks more like wind stuff to me than anything. But anyway,
they've been moved across. The other thing, you think about these nice, neat footprints, how would you form them in a dry desert sand? There's no cohesion between the sand grains. The conventional paradigm says, oh, well, maybe there was the dew in the morning that held enough.
Don't even need the dew in the morning. You just need very slightly damp sand. It can be almost dry. I think that moisture content in my demonstration was 1 to 3%, something like that, which, just because it's dry and in a desert just means, there's not a lot of precipitation. Antarctica's a desert, It doesn't mean it never rains. It doesn't mean there's no groundwater. This stuff is probably really close to sea level anyway. You probably had relatively shallow groundwater compared to what you think of in the middle of the Sahara at, 300 kilometers above sea level.
Water. But that dries out very quickly. And then you get more sand, dry sand, and it tends to distort. These are sharp outlined.
Yeah, and if they were made quickly and covered quickly by wind-blown sands, which can move a lot quicker than water lane sands, and water is going to mess it up if there's any current, especially current moving at 2 or 5 meters per second, Snelling. He's conveniently leaving that out. Yeah, their models are ridiculously fast water currents. And all this stuff is tranquil. Like I said, you see worm burrows in it. This is just nonsensical. It relies on your ignorance.
And it's exactly what you find in cubic grand staircase, also from observation. So that's real details from around the area that are found in another area. But we can build up this concept of all this sequence of layers into the geologic column by piecing together.
There's no such thing as a geologic column, although it has sneaked its way in. It's a combination of two terms. It was used. I did find one reference to it in one publication in the 19th century. But once we decided, that's it. I've never seen it written anywhere else. It doesn't mean there might not be, but it's 19th century. They didn't have they didn't necessarily separate but anyway, I'll get into that in my time video. But geologic column is something young Earth creationists use to get you off track. It's stratigraphic column or geologic time scale. The two are often side by side, but they're both independent of one another.
Together the details from around the world. Here in the United States, we've actually found, if we got all the local geologic columns from drill holes and from
I just showed you a bunch of ones that don't match up his stuff, and I really wish I could see what was over here. But you can just see just from these, whatever this is a mix mash of, because they're not telling you, you can see the units are not continuous. And like I said, this is oversimplified too. These are columns. They're not cross sections like that thing I showed you with intertonguing units.
Observations. So that's real physical layers. And then match them from air.
So you even see intertonguing here, because rock units can intertongue. You even see transgressions here. And they're not telling me what these are from.
To area around the.
But can we see this here? I don't know what any of these are. Chesterian, because I'm not a Phanerozoic guy. But anyway, it doesn't matter. The point is, nice reference there, and that's an epic fail.
United States, we actually can break down the geologic column. There's
no such thing as the geologic column.
Section that contains all the fossils.
And they're showing you all these things. Oh, this is Illinois. Okay, and this is Michigan Basin, East Interior Basin. There's Indiana, Ohio. This is pretty much the limit. So yeah, you can even see they're telling you all this while they're showing you something that's completely counterintuitive to what they're saying.
Into 6 major sequences of rock layers.
But if you don't know that, then whatever. Yeah, there are 6 major.
Called mega sequences. This has been known for over 5 decades.
Yeah, even longer than that.
We can trace them right across the continent as if they're...
Yeah, but these are sequences. This is not lithostratigraphy. This is something called sequence stratigraphy, something different. You're going to have different rock units mixed in with sequences or mega sequences. You're not going to have continuous lithological units. These are not lithological units. These are the results of transgressions and regressions. And if we had one massive global flood, wouldn't you see one mega sequence? And there's not just 6 in the Phanerozoic. That's just what's in the U.S. There's less and more in other places. So this is just gobbledygook.
There was a sediment rush surge that laid down these layers, and
he's using leading language, surge, rush, when you don't need any of this. And he's giving you a little bit of science, not even as much as Whitmore did. But this is what they do. They give you tidbits of science, actual science. And then they use terms they made up, or 19th century terms. So if you Google it, it's going to come up with their nonsense, like erosion marks, geologic column, although, like I said, that's reworked its way in because of these people. And, bent rock. You're going to see their stuff, and they do this on purpose. We don't say bent rock in geology. Well, in an introductory class, we might. It's deformed rock. We don't say erosion marks. We say, we just talk about disconformities, nonconformities, or soul marks, stuff like that. We don't sit here and use these terms, and they know this. They have to know it. But anyway, this is what you notice. These are all fast boom, 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 boom talking points, and you've seen how long it's taken me just to show you other stuff. It's just he's firing at you like a gish gallop, but this guy agrees with him, so it's not really a gish gallop. I have to stop this to give you anything meaningful and show you stuff. If he just threw this at me, I'd have to wait for him to get done talking, take notes, hopefully I catch enough, and then probably miss stuff, because this is what they do. And notice he's arguing. He's not presenting evidence. I'm not seeing anything. And what we have seen in published strat columns and other things that they've shown is counterintuitive to what he's saying. Like I said, Snelling's a petrologist. He's not a stratigrapher. He's not a structural geologist. I know that. The guy has a hard time picking out a fault. I'm not dinging him, but that's true. This Grand Canyon paper, he shows a cross-sec or a photo of, what was it, Carbon Canyon or something like that. And there's a fault there and a hard, deformed, looks like a syncline, but I don't know, because he didn't put any measurements in. He didn't draw any lines to explain things. He just said dropped a photo and said, hey, here's this then. So that tells me Snelling's probably not the kind of person you want to take in the field to make a geologic map to begin with.
It's interesting, within each mega sequence, you actually go from a coarse layer at the bottom. In the Grand Canyon, you saw the Tapete sandstone. Yes. Sitting on top of that is the Bright Angel shale. Sitting on top of that is
Bright Angel shale, the limestone. That's what we see in a typical transgressive sequence. And the limestone, these are, either chemically derived or derived from living things in the Phanerozoic. So this is doesn't have anything to do with. This is a chemical biological unit. These two are clastic sedimentary units, and they used to divide these up in the 19th century into aqueous and other things. It's totally cool and weird, and I'll show that in a future video. It has nothing to do with these guys.
The Muave limestone. So the grain sizes get finer as you...
And why didn't you continue up, Snelling? There's other units up here. Why didn't you do that? I wonder why. Maybe because it doesn't just keep fining upwards. And I can take you to places with coarsening upward sequences, like the Oronto group in the Upper Peninsula, which is actually older than their flood, but is unmetamorphosed classic deposits that fill the mid-continent rift. And you get a fining upward sequence. You get your Conglomerate Falls member, which is coarse. It's all boulders and cobbles, which there's none like that here. But anyway, then you get sand starting to come in your Gorge Falls member, and the class get a little smaller. Then you get into the Sandstone Falls member, and you get a lot of sand, fluvial river deposits, but then you start to get alluvial fans coming in again, so you get more pebbles and conglomerate again, before finally giving way to the Union Bay member, which is more fluvial deposits. It looks a lot like the Freda Formation way above it. So this doesn't happen everywhere, and not to mention the Oronto group is supposedly before their great unconformity. When I don't want to say before, because the great unconformity is a thing; it's just not consistent everywhere, nor in North America. But that's below that; it's Precambrian. Yet we had a sedimentary environment going on there. But if you don't know the geology of the continent or anything, you're not going to know he's full of it.
Go up, and that's a recurring feature of these mega sequences. And the best way to explain it is with the flood paradigm, not millions of years.
No, it's not the best way to explain it. And they say not with millions of years. We don't do geology based strictly off chronology. The chronology was born from the rocks. Okay, and granted, before we had radiometric dating, we didn't know. And in Europe, and you're going to see in my time video, Europe was more focused on the time aspect. We were more focused on trying to tie the rocks into the time aspect before we gave up on it and realized, we didn't give up on it, but realized that you can't strictly do that because lithological units contain change. We developed lithostratigraphy, and that's how we map things. We don't map things based off millions of years, Snelling. We don't do that. It also depends on your scale, how far zoomed in you are, how far zoomed out you are. Scale matters.
And so we see that. There's a real sequence of rock layers that we find.
By the way, his coquina is way above his Muave limestone. So then you got more sandstone above that. See, conveniently leaving stuff out.
Around the world. The layers that were formed and add in millions of years.
See if we can get to a model.
On the flood paradigm. But then there were geologists like Murchison.
He actually will come up in my time video.
And Sedgwick and Lyell.
These guys as well.
Who started to subdivide some of these layers and add in millions of years and give them...
They never did that. Those guys had no idea about how long it took to deposit this stuff. We don't start pulling numbers until we get radiometric dating. And I'm going to go into that in my time video. 1925. It's the first time we start to see this stuff. And they're wrong. Back in those guys' days, some guys thought the earth was a few 100,000 years old. Some guys thought it was 100 million. No one had any idea it was 4.5 billion years old. And these guys were not anti-Bible. That's bullshit young earth creationists put. Matter of fact, they went out looking for evidence of the flood because that was the only guide they had. So I can't blame those guys. They had nothing else to go by. But I can blame Snelling because he knows better. And let's just see where this goes.
Names like the Cambrian from Wales and Ordovician from a Welsh
Ordovician came later. Originally it was Cambrian to Silurian.
tribe, and so they started to give these names to the layers.
Yeah, because in Britain, Europe, they focused more on they got these names out of layers, but those aren't even the first names. They got the layers, but then they started focusing on time, Cambrian, Ordovician. They were more time-oriented. Here we were more rock-oriented.
Those labels do mean a particular package or group of layers, but they don't necessarily mean millions of years.
They're not even the same span of time, Snelling, and just open the bloody GSA geologic time scale for crying out loud.
The issue of establishing millions of years is a separate question that we've been dealing with. We've talked about the radioisotopes. We've talked about the extent of these layers. And
you haven't talked about radioisotopes.
All those other evidences in the
Here we go again, guys. Bit of advice. Young Earth creationists, if you say the word evidences to me, I know exactly who you got your stuff from. Evidences technically is not wrong, but it's said on the other side of the pond. It's not said here. Evidence in and of itself is plural. So if you say evidences, I'm going to know you got your stuff from here in AIG. I'm going to know that's where you got it from.
Geologic record indicate that they weren't the millions of years, but this is because there's a clash of views of Earth history. Those who want to have the conventional view of millions of years versus those of us who say no. Most of these layers form rapidly within.
There's no dichotomy. No geologist worth his salt is going to... I'm going to get gigged for saying this. Is going to sit there and side with these guys. And I'm not insulting Snelling's degree. I'm not insulting his abilities as a petrologist. He's actually pretty good at it. I'm not doing that. But there's a reason why these guys publish only in their own stuff and write books. Because anybody can do that. Now, Whitmore does have papers, and I showed you one of them, in more conventional stuff, but it doesn't say what Snelling's saying. And like I said, water lane of the Coquina or wind lane, it means nothing for young Earth creation. It's irrelevant for it. So, let's just let Snelling finish.
In the year of the flood.
So it isn't a difference in believing in those layers that exist.
Not at all.
It's the difference of time, isn't it?
Correct.
How are you going to deposit all this in a year without violating the known laws of physics? I mean, you have to interject miracle. You have to. And once you do that, you're no longer doing science or geology. You've entered the realm of fantasy and philosophy. And I know science came from philosophy. I don't give a shit. It's not the point. So I'm getting cynical, and I'm thinking about everything Snelling has said, and I'm just like, I'm thinking about the poor person who doesn't know any geology watching this and just swallowing everything he's saying. And yeah. Like I said, I'm not bashing Christianity when I do these. I'm not bashing anyone's religion. I'm not doing that. It's not my goal. But when you try to do pseudoscience and sell it as science, then we got a problem. And that's what this is. And Snelling's like me. He can get very passionate. You can see his hand gestures. I do that too. So I can't ding him for that.
And so it's not a question of science versus the Bible. It's a question of different views of Earth history.
I'll give him that. That's actually a decent statement. But where did you get your view of Earth history from, Snelling? You got it from not necessarily even the Bible. You got it from that bishop's old interpretation. I forget his name. Someone tell me. My brain's fried now. My wife's about to get home and we're going to go have dinner. But anyway, so we're going to wrap this up. I hope that was helpful to you. Like I said, my intent is not to bash anybody, but if somebody's leaving stuff out or telling you something incorrectly, I am going to let you know. I don't like to use the word lie because I know Snelling is not a stratigrapher or structural geologist. He's a petrology guy. He's also knows nothing about the North American Stratigraphic Code. I found that out as well. But anyway, that doesn't matter. What does matter is you've got to sit here and ask questions past just what you're being told. Now, when you're in grade school, and even high school, unless you're in an honors program, college bound, which I wasn't. I got into college the hard way because I said I was never going to go, and I did. But anyway, you're taught what we know. That's the point. You're not taught the how do we know this. You don't find that out until, I hope that wasn't a lie. You don't really find that out until you get into college or you start looking into stuff for yourself. If you get to college and start doing geology, start going in the field, you're going to know how we came to these conclusions. And we didn't just pull this stuff out of our back ends. That's not what we did. This was a long, difficult process, and we aren't even there yet. We're still refining things. Geology isn't in this just refining. We're discovering new stuff all the time. We have big unanswered questions like, when did plate tectonics start in Earth's history? That's a big unanswered question. We still have these things. But anyway, that's it. If you have any questions or comments, guys, please leave them below, and I hope you learned something.